Greetings, the Astro 30 here yet again, and welcome back to AEL. Now, the other day I reached over 5,000 subscribers. Thank you very much for subscribing, it means a lot to me. And if you're new to this channel, consider adding me a sub. My next goal is to make 10,000 subscribers by the end of 2026. Let's see if we can make that happen. Well, today I'm going to be looking back at the Elektor PA300's protection circuitry of the project, which I did not include on the main power amp PCB, which is now being manufactured and is on the way but is not here yet. My main goal is I want to do away with the first comparator that is used as temperature sensing because, well, the part that he's used is a positive temperature coefficient, or PTC, thermistor that will increase its resistance with heat. I modified it round to use a negative temperature coefficient, or NTC, which its resistance will decrease with heat. But I thought the easiest way to get overheating protection is just to use say a 100 degrees Celsius normally open temperature switch, which can mount directly to the heatsink, which means all we have to do is connect where this ground sense pin is, which is where the rest of the circuitry goes, like the DC detection, loss of ASD detection, etc. connects to, is probably through a diode, is connect one end of the switch to the cathode of the diode, the anode connects to here, and the other side connects to ground. And as soon as the switch closes due to it heating up, well, then it will bring ground up into here, turning this comparator off. So that leaves us with one problem. We end up with one side of the LM393 not being used because it's a dual comparator. You can get single comparators, but they're a little bit more janky to use. So what I thought of doing was using the common NE5534 as our main comparator for the delay circuitry and see whether or not it can work the same way as the LM393. Albeit I've got to be aware that there are protection diodes on both these inputs, and there might be a small finite bit of DC offset also on those two inputs. So I don't know whether this diode is necessary or not, but because I had issues with the LM393 with the LED still being illuminated, well, I've included the diode anyway. So let's flesh this up, and I'll just have a fly wire off here for the ground sense, which I can just connect to ground, and we'll see if the circuit works. So there's the circuit built up there. It currently is off. I'm using a BC549 as the driver transistor to the relay. Got a 120 ohm dropper resistor for the relay because it's running off 15 volts. Yeah, it's only half watt, but it's big enough for the current limiting required for the relay, with our flyback diode with the leads going off to the relay connected across it. The LM3, not the LM3, the NE5534 is just there with all the rest of the circuitry there, and there's our protect, or it's in protection mode LED there. So if I turn the circuit on, the LED lights and then it goes out. So yes, it does operate the same way as the LM393, which is great. So let me take my fly wire, which is here, and touch it to my ground point, which is the negative of the circuit. Relay drops out, LED turns on. Let it go. It resets. Okay, however, I did find out something very interesting. If this diode is not in circuit, well, let me demonstrate rather than talking about it. So I'll take a clip lead. Actually, no, yeah, I'll take a clip lead. Just got to be careful it doesn't short things. And I short only the diode out. Okay, so that diode is now essentially out of circuit. If I turn the circuit off to reset it, all seems normal, the relay came on. However, if I touch this now to negative, well, the light comes on and the light goes out, but the relay never drops out. Interesting. The op amp itself must be providing about 0.6 of a volt to the base of this transistor to allow it to turn on. So I'm going to hook up my multimeter between ground and the base of this transistor, and we'll just see what sort of voltage we've got there. Okay, with the circuit still turned on and the relay energized, we've got roughly 0.8 of a volt there at that base after the 33k resistor, so directly at the base. So if I now bring this pin 3 of the op amp basically to ground, yeah, there's our problem. We're still at 0.68 of a volt, which is enough to keep that transistor turned on. So I'm not 100% sure if that's going to be affected by supply voltage either, but let me just disconnect that shorting wire so that the relay drops out. Okay, with the relay engaged, we're about 0.82 volt, which we were before. With it grounded, we're still at 0.6 odd of a volt there, which is, yeah, probably going to be a little bit of an issue. So I know that the op amp will operate up to about 30 volts, so I'm going to increase the supply voltage to about 18 volt, 16 volt. So our voltage has come up. So if I ground this, it still drops out. Okay, alright. So if anything, I may want to increase this base resistor from 33k to maybe 47, just to bring it down a little bit, just to account for maybe it's not going to be quite at 15 volt, it might be slightly higher. Let me swap that out and we'll see what we get as a difference in results. 47k is in, so you can look at the meter whilst I apply power. Not much difference there. Didn't really make any difference. So, yeah, okay. So currently that's the voltage at pin 6. If I bring the input to ground, well, it drops down to more like 1.4 volt on the output. Okay, that's fair enough. I might up this a little higher. I've just got to be careful of that relay, I don't burn it out. Yeah, it's more at 1.5 volt now on pin 6. Okay. But it looks like the diode is necessary for the circuit to operate correctly. And as this will be operating at a 15 volt supply rail, I don't see any issue with it. So that might be what I'm going to be doing when I design the power supply for this power amplifier, is using this current circuit that I've got here, because it seems to work, with the diode. And as I said, have a diode with the anode facing pin 3. Just checking things for heat. With the anode facing pin 3, and the cathode will connect to, well, LED indicator for thermal overload and ground, with a normally open thermal switch. And the rest of the circuitry that comes before us should work just fine, because it's basically switching ground, so it's just doing the same thing as me shorting pin 3 between this potential divider here, voltage divider here, to ground. In the same fashion. It's not really doing anything else spectacular. There should be no like collector loading from the transistors on it. However, what I might do is I might include what I was talking about with that extra diode and the LED indicator, and I can mimic the thermal overload section. Alright, the extra components are in. I've got a wire coming off pin 3 to the cathode of this LED, 3K3 resistor on the anode going to positive, and from the cathode point, which is pin 3's input, we've got our fly wire. I have forgotten a diode, which might also be helpful, so just give me a second to correct that. Diode is in, circuit is currently on, and if I connect my fly wire, which is at the cathode of this diode, to negative, well, the thermal LED comes on, relay drops out, protect light comes on, goes out, resets. And that was basically doing the same thing as the first comparator in the original circuit was doing, except now we're using a bimetallic switch, which is normally open, to do the temperature sensing. And the reason for the diode is so that we're not allowing a current path to the LED when the other detection circuitry, such as the DC detection circuitry, brings pin 3 to ground, so it's giving a current path for the LED to light up to ground, which is not what we want. Because if this was just connected directly to our LED without the diode, without shorting on stuff, as you can see, the LED is permanently lit because there is a current path now to ground via the op-amp circuitry via pin 3, which is not what we want to do. So that is the purpose of that diode, which gets rid of the fact that the light is on, but will only light or have current available to it when that part of the circuit is brought to ground. Neat! So there we go. I think that's pretty much as simplistic as I can make it. So there's the changes to the schematics, so it's got a little bit of clarity here of what I'm talking about. This line here that's marked off, that goes to the rest of the circuit, which is the 2 transistors for detecting DC and plus our loss of AC detection transistor circuit. And both of those circuits are isolated from this side of the circuit by this diode. Both these two diodes are 1N4148. I've actually drawn this one backwards, by the way. Please excuse me. There we go, that's better. Now it's the correct way around. These two terminals here marked N/O means normally open, so that's our thermal detect switch. 100 degrees Celsius would be about probably right, because usually the junction temperature of most output transistors, or any transistor for that matter, is around about the 120 degree mark to 160 degree mark, depending on the data sheet, before they fail. So having a heatsink on such a power amplifier, such as what it's going to be protecting, up to 100 degrees Celsius is quite significantly hot. That's to the point where you can't even touch the heatsink. So I think setting it at 100 as the cutoff point will work just fine. So there we go, using an NE5534 op-amp as the comparator instead of the LM393, and everything else looks like it works just fine. Now you may be asking yourself a question as to why do I still want to use a comparator just for the delay circuitry part? Well, the simple reason is I want to keep the circuit as close to the original as possible for nostalgic reasons. I mean, yeah, add a few modifications in here, make it function a little bit better, etc. But yeah, I want to keep it close to the original design as possible. So that's why I elected to still use a comparator, or in this case an op-amp. Of course, no one on this channel watching this would forgive me if I didn't actually bother to test that the rest of the detection circuitry was going to play nice with the op-amp. So I have done that. Now I've got my loss of AC detection circuitry up here, which is connected to a power supply on its negative. The positive of that power supply is going to the ground point of the circuit, which gives me a handy negative reference to test the DC detection circuitry up here, so I can see whether or not it detects a negative voltage potential, as in the case of the output transistors failing and shorting, bringing one of the supply rails up to the output. So I'll turn the first supply on, which powers the op-amp circuitry, and as we can see, that LED is illuminated, but the relay has not come on. That's because our DC detection circuitry is now connected, which is holding pin 3 low currently. So if I turn the second supply on, there it goes, the relay engaged. So now I've got this fly wire just sitting about, which I can touch between either the positive part of the circuit which is coming into the op amp, or that secondary supply's negative point, and see if the relay drops out accordingly. So you can watch the LEDs, and I will first bring this to the positive rail. Drops out, release, resets, and now I'll put it over to the negative side of the circuit, which is going into the loss of AC detection. It's a bit slower, but it does work. Release, and there we go, it resets. So yes, it works, but why is this op amp only going as low as 1.4 volts on its output when it swings low? Most likely because of this particular op amp cannot swing close to the 0 volt rail. Would a TL071 work better in this situation? I don't know. I don't actually have one to test that theory with. The LM393 itself probably would have worked okay without this issue, but yeah, it is what it is. So as long as we keep this base biasing resistor, which goes to this transistor here, to around 47k and no lower than that, it should be fine under most operating conditions. Actually, what I want to see is if I rotate my supply down to 12 volts, whether or not the circuit still operates, assuming on the worst case scenario that if we use, say, a Zener diode and drop-in resistor to give us the 15 volt rail here, that it holds it down for some reason. Does the circuit still operate? Let's find out. Yes, but it's a bit slower to re-engage the relay, but that's fine. Negative. Yes. Yes, it works. Okay, so I'm going to measure what output we've got now at pin 3 when it's in the off mode, i.e. that the pin 3 is brought to ground. So I need to somehow get this to ground and measure across, well, this, I suppose after the diode will be fine. We can always add 0.6 of a volt to the reading. So currently we're not in protect mode. Now we are. Brings it down to about a volt. Add 0.6 of a volt, it's still 1.6 of a volt. But it's enough for the base voltage of that transistor to be stolen enough for it to not engage the relay. So, okay, this is probably about as far as I can test it. There's not much else I can really do. I mean, I can just test to see whether or not this thermal overload circuitry is still working after messing around with it. So I connect that to the anode, connect that to ground somewhere. Yes, it does. Okay, excellent. So the circuit works. And that's probably the circuit I'm going to be going with. So let me redraw up the schematic properly on a bigger whiteboard so we can see how it all comes together. And there it is there. As messy as that is, that shows basically how the whole entire circuit is wired. So this resistor here, which is marked RZ, that's a bad Z, my apologies, RLA, as well as this 100k input resistor which comes up with the amplifier's output, they all should be 1 watt devices. The rest can be quarter watt, half watt, it doesn't really matter, because this is all low current anyway. Anything marked 546 means BC 546, 4148 means 1N4148, and anything marked 4004 means 1N4004. And I've marked the Zener as 15 volt because I can never remember the bloody number of it. I think it's 4744, I believe, maybe 4746, whatever. Anyway, it's marked as 15 volts, so it's a 15 volt 1 watt Zener. The relay goes through to the VCC main power supply point that goes to the power amps. So this value of resistor is calculated based on the resistance of the coil, the current consumption of the coil, and it being a 12 volt relay. RZ, well, probably can be the same as it is in the original schematic, 3.3k, 1 watt device. And over here we've got our 100 degrees Celsius normally open thermal switch, which is optional now, so you don't actually have to include that to make the rest of the circuit work. So when I go to route this out as a PCB, which I'll do over the weekend, these will be optional, so you wouldn't have to install this 3K3, this LED, or the terminal connector for here, and you just have, you know, your normal input detection part which comes off your power amp, and of course that goes over to the center of the relay's contacts, and then the amp comes in over there. I just haven't drawn that in for simplicity, and the normally open side of the contacts of the relay goes out to the speaker. As I said in a previous video on this, the reason I left it off the main amplifier board because it made the routing of the amplifier board complex, and also I said that it really should be the job of a separate PCB or part of the power supply circuitry. So that's my decision. I'm going to make it part of the power supply circuitry. So one power supply module powers one amplifier module. Oh, I've marked over here because someone was confused in the last video I did messing around with this circuit in the first place with the AC sense pin. They were thinking you connected it to the wall socket side of the amplifier, the 240 volt mains. Yeah, no, don't do that. One, you'll kill that transistor. Two, you probably blow the arse clean off of the comparator, or in this case the op amp. And well, this 470 nanofarad is only just like a normal MKT capacitor, which is only rated at 100 volts. So if you put 240 volts across that cap, well, expect bad things to happen with that capacitor as well. So no, I've put in brackets here secondary. It comes off the secondary side of the transformer, one of the windings. Before I forget, we'll notice RAC here. That's the resistor that goes to the AC sense side circuitry from the secondary of the transformer. Now on my breadboard that's currently 47k because I'm dealing with a pretty low voltage of 17.1 volt currently. In order to make this circuit work any higher, and the relay would not be allowed to be engaged because it would be holding, well, it wouldn't be holding this base low enough to steal the bias voltage from the 47k resistor above it. On the PCB in the final, if you were to run this on, say, a 25025 volt secondary transformer, well, that resistor value should be more like 68k. If you were running at 30 volts AC, like 30030, that'd be more like 82k. 35035, which gives us a supply rail of about plus minus 49 volts, is going to be 100k, and the maximum I think that this should run at, or the power amp should run at, is plus minus 56 volts, which is a 40 volt secondary transformer. Well, the original circuit had a 120k resistor here, so it'd be more likely the 120k for that particular voltage potential from the secondary of the transformer. So that'll be documented on the PCB with the PCB once it's produced and I've had it made and, you know, tested out on this channel. So I'm happy with how this circuit is operating. It could probably be improved. I mean, you've got the slow reaction time from the negative potential compared to the positive potential for when the relay drops out, but that's mainly because of the fact that it's got to go through this emitter junction first and then through the collector junction. So it's going through the emitter base collector. So you got 1.4 volts drop roughly there, 1.6. So it's going to take a lot longer for it to start conducting before it actually pulls the pin 3 of the comparator low. But with a higher voltage potential, say the VCC line, plus minus 42 volt for instance, well, it'd probably react a lot quicker because the potential is higher. We're also dealing with the time constant it takes to charge this capacitor before this circuit will react. So in the real world it may appear slow, but to a speaker will handle the DC potential on it for a short period of time before it starts to smoke from the voice coil, and maybe, if it doesn't blow the speaker right away, set the cone on fire. But it should be quick enough reaction time here for it to save expensive loudspeakers from complete damage. That's the theory anyway. The circuit could be improved a little bit better than it is, but I don't know, leave your thoughts below. So I'm going to leave this video right here. I'm the Astro 30, and if you enjoyed this video, please remember to go down below, like, comment and subscribe if you haven't done so already. And as always, this is the Astro 30 saying see ya, thanks for watching, have a great day.